So the second part of today's lecture is concerned with partitioning of problems into hardware and software parts. So, like in the previous lectures, we are still in the chapter 6 of the accompanying textbook on application mapping. So when we start off with hardware-software partitioning, we see that as hardware gets more powerful, for a given problem we start off at a given year with an implementation that has to be executed 100% in hardware, and as hardware gradually gets faster, we can afford to implement more and more parts of the solution in software. So here it's denoted for a time of 10 years, and we've seen while starting off in 2010 with a 100% hardware solution, in 2020 or about, we could implement a solution 100% in software, taking advantage of the fact that processors are getting faster and faster. However, this assumption is only correct for fixed functionality. In general, we cannot assume that this will work out. So Deman has formulated that for video encoding and decoding, by the point in time that a version MPEG-N can actually be implemented completely in software, the follow-up version of that standard MPEG-N+1 has already been invented, so this cycle starts off all over again because you have higher resolutions, you have higher computational requirements, so you start off again with a 100% hardware solution and gradually go down, but at some point in time the next standard takes over, which again requires more and more resources. So the question is, which part of the functionality of a system, as we are right in the middle here between hardware and software, has to be implemented in software, which has to be implemented in hardware in order to achieve the performance we require of such a system. Now, so how do we decide which functionality to implement in software and which functionality to implement in hardware? We can make this decision based on hardware-software partitioning, which is a special case of hardware-software co-design. So we start off with a behavior of the application in question and a description of the platform we want to execute our application on. Now we start off partitioning the problem into a hardware part and a software part. So the hardware part uses hardware synthesis to derive an implementation, whereas the software part uses a compiler to derive an executable binary. Both together are put into a simulation system, and then we check if the performance requirements of our system is met. If these performance requirements are actually met, we can stop this iteration. Otherwise, we just input this solution as a decisioning factor for the next partitioning and start off with a different partition of our system. And so we cut the system in half between hardware and software pieces. So one example for hardware-software partitioning is the so-called co-design tool COOL. And as we've seen previously, the inputs to COOL are the required behavior, which is the third point on that list, the target technology we want to implement our hardware on, and the design constraints for our system we want to use to evaluate the design decisions here. So the approach is to start off with a behavioral specification. So you have some time constraint you have to fulfill, you have some inputs you provide to the system, you have some output you want to generate, and you have some functionality in between, which is dependent in some or other ways. And so we can deduce a mapping here. So for example, in this case, we can actually map the functionality FCT1 to processor 2 and the functionality FCT3 also to that same processor, perhaps since the data flow is directly between these processes here, and on the other hand, the lower part of that data flow here, FCT2 and function 4, is being mapped on processor P1, whereas the final functionality, function 5 here, will be mapped to hardware. So the COOL partitioning algorithm consists of several steps. In the first step, the behavioral model of the system is translated into an internal graph model. Then in step 2, the behavior of each node, which is described in the VHDL hardware description language, is translated into an equivalent C description. So in step 3, we start compilation. All of the C programs we've built above are now compiled for the target processor. We compute the resulting program size for each of the C program, and then we estimate the resulting execution time. For this we might need simulation input data because some of the algorithms or some of the parts here may actually be input dependent in their runtime. Then in step 4 we can synthesize the hardware components of the system. So for all of the leaf nodes we require that we synthesize application specific hardware. This is possible nowadays since high-level synthesis tools are sufficiently fast. Now in step 5 we start flattening the hierarchy of a system. So the designer of a system sets a given granularity, which is maintained here, and we add cost and performance information to the nodes we determine here. For partitioning, we might need very precise information, and this precise information is pre-computed already here in that step. Now in step 6 we generate and solve a mathematical model of the optimization problem. So we generate an integer linear programming or ILP model for the optimization, and this is optimal with respect to the cost function, which approximates the communication time in a system. In step 7 now we apply iterative improvements. So we can map adjacent nodes to the same hardware component. Actually we can merge these nodes, so we see task 3 and task 4 on the left side can actually be merged to task 3 asterisk on the right side, which run on the same processor P1 here. In step 8 then we can perform interface synthesis. So after partitioning our problem we need some glue logic to make all the parts of our system in hardware and software to be able to talk to each other. So we build all the glue logic required for interfacing the processes in our system, the application-specific hardware, and the memories we generated for that system. Look at the integer linear programming model that's used for hardware-software partitioning. So let's start off with a notation. We have an index set V that denotes the graph nodes of our task graph. We have another index set L that denotes the nodes types of our task graph. For example, it might be a node that executes a square root calculation, a discrete cosine transformation, or a fast Fourier transformation. Another index set M denotes the hardware component types. For example, we have hardware components that can execute the discrete cosine transformation or the fast Fourier transformation. The index set J is the index set of hardware component instances, and we have an index set KP, which denotes the processors in our system. And for simplification, we assume that all the processors of our system are of the same type. Now we can define several variables for our ILP model. And the first variable is x with the index v and m, and this is equal to 1 if and only if the node is v mapped to a hardware component type m, which is in the set of our hardware components. Otherwise the value of that variable is 0. The next variable, y of v and k, is 1 if the node v is mapped to a processor k out of the set of our processors, and 0 otherwise. The next variable is ny of l and k. This is 1 if at least one node of a type L is mapped to a processor K, and 0 otherwise. Then we have a mapping called type, and this maps from task graph nodes to a type of a task graph. So it's a mapping of the set V to the set L. And finally we have to have a cost function that accumulates the cost of all hardware units. So cost function C is the sum of the cost of the processors, of the cost of the memories, and the cost of our application-specific hardware in the system. So for our ILP, in order to get optimal solutions, we have to define some constraints. And the operation assignment constraints said that for all of... Okay, das ist V. Task graph nodes. So now we have to consider a given set of constraints, and the first constraint is the operation assignment constraints, and this said that for all of the nodes in the task graph, the sum of the hardware components over all of the hardware components of the system the problem is assigned to, plus the sum of the processors over all of the processors in our system this task is assigned to, is 1. So in other words, this means that all task graph nodes have to be mapped either in software or in hardware. In this solution here, we assume that all variables are integers, since we have an integer linear programming problem, and we can set additional constraints to guarantee that the variables are either 1 or 0. So for all of the task graph nodes and all of the hardware nodes, x, v, m has to be less or equal than 1. And on the other hand, for all of the task graph nodes and all of the processors, again, the mapping y(vk) has to be less than or equal to 1. The next operation assignment constrains the type of operations. So for all types of operations and for all nodes that have this type of operation, if that operation is mapped to some processor k, then that processor must implement the functionality required of L. So again, these decision variables have to be 0, 1 variables. These additional constraints apply for the resources in the system and the design. So for all of the hardware components, the cost of the components, which is expressed as an equation involving the area of the components of a given type M, is equal to the sum of the costs of the components of that type. And this cost should, of course, not exceed the maximum cost available. Now for all the processors, the cost for the associated data storage area should also not exceed its maximum, and for all the processors, the cost for storing instructions should also not exceed the maximum available. So the total cost, sum over all of the hardware components, should not exceed the maximum that's available. The total cost of data memories should not exceed the maximum, and also the total cost of instruction memory should not exceed the maximum available. And start the scheduling. Here we see a task graph with different task graph nodes starting from V1 to V11 here, which all are executing different functionalities. So we have 4 functions V1 to V4. We have these circled functions V1 to V5 to V8, and we have this octangular functions V9 to V11, which are each of different classes here. And so now we can start off and say we have a system consisting of one processor P1 and an ASIC H1, which has 2 hardware functions for a finite impulse response filter FIR1 and FIR2. And these are interconnected by a communication channel. And now we can see the scheduling here. We can say that the functionality of V7 and V8, those 2 task graph nodes, is mapped to processor P1. The communicating functionality of the nodes V3 to V7 and V4 to V8 are these edges here in the graph. So these are mapped to the communication bus. And V3 and V4, maybe FIR filters, these are mapped to the ASIC we have in our system. And now we can determine different execution orders here. So we can say that V3 is executed before V4 or the other way around, since they are sharing the same component here. And for the processor, again, we can say that V7 is executed before V8 or also the other way around. And the same holds true for communication then. So if V3 is executed first on the hardware component and V7 is executed first on the processor, of course we need communication between V3 and V7 to take place first. So E3, the communication, takes place first on the communication channel. So in the previous example, we've seen that we have precedence constraints. And now if we consider task nodes V with index I1 and V index I2, and these nodes might actually be mapped to the same processor or hardware component instance, we will introduce a binary decision variable B with indexes I1 and I2. And for this variable B, we postulate that it is 1 if task graph node I1 is executed before task graph node I2 and 0 otherwise. So now we can define constraints of the type: the end time of V1 must be less than or equal to the start time of Vi2 if that constraint B is equal to 1, and it's the other way around if B of I1 and I2 is equal to 0. So now we have to ensure that the schedule for executing operations is consistent with the precedence constraint in the task graph. And this approach then fixes the order of execution of the tasks. In addition, we might have other constraints, like timing constraints, to guarantee that certain timing conditions are actually met. And there might be even other constraints which we omitted here for the sake of simplicity. Now let's look at an example for the cool algorithm. So we start off with a system consisting of hardware types H1 to H3 with costs of 20, 25 and 30 respectively. And we have processors of type P. And we have 5 tasks with the execution times we see in the table below. So For task 1, on hardware 1, we have an execution time of 20. For task 1, on the processor, we would have an execution time of 100. Again, for task 2, this can be executed on hardware unit 2 with a cost of 20, or on the processor again with a cost of 100. Task 3 and task 4 each can be executed either on hardware unit 3 with a cost of 12, or on the processor with a cost of 10. And finally, task 5 is identical to task 1 with requirements of 20 time units on the hardware unit 1 and 100 time units on the processor. So now we can calculate our operation assignment constraints. So we know that for each task graph node here, the sum of the hardware plus the sum of the processor components it's mapped to must be 1. So for example, we can say that task 1 can be either mapped to hardware 1 or to the processor. So x11 plus y11 has to be 1. For task 2, we can map it to hardware 2 or to the processor, so x22 plus y21 has to be 1. And again, tasks 3 and 4 can be either mapped to hardware 3 or the processor, so the equations for index 3 hold true here for tasks 3 and 4. And finally, for task 5, it can either be mapped to hardware 1 or to the processor again. Assume that the types of tasks are of 1, 2, 3, 3, and 1 respectively. So we know that for all of the types of tasks and for all of the nodes, the type of that node has to be executable. Of the processors, we know that at least one of the tasks of that type is mapped to the processor. So we know, for example here, that functionality 3 is to be implemented on the processor if node 4 is mapped to the processor. So here we generate a mapping of the functionalities to be executed to the processors that execute that functionality. Now we can add timing constraints to our system, and these timing constraints can lead to the assumption that application-specific hardware is required for time constraints less than 100 time units. So the cost function here is cost is 20 times the number of hardware units of type 1 plus 25 times the number of hardware units of type 2 plus 30 times the number of hardware units of type 3 plus the cost of processor and memory. And now we can determine the result here. For a time constraint of 100 time units and a cost of processor that is less than the cost of the hardware component 3, we can determine a solution which we here demonstrate by educated guessing, and this is a mapping of task 1 to hardware 1, of task 2 to hardware 2. Since we have to fulfill a timing constraint of 100 time units, we cannot afford to map any of these tasks with 100 time units on the processor to the processor itself. So essentially also task 5 has to be mapped to hardware unit 1 again, and we can map task 3 and task 4 to the processor, since the execution time on the processor for these tasks is only 10 time units. So we end up at this task graph here with task 1 mapped to hardware 1 and so on, and we see that task 3 and task 4 are both mapped to the single processor in our system. Combining scheduling and partitioning is a very complex problem. So we can use a heuristic here. We compute the estimated schedule by performing the partitioning for that estimated scheduling, perform the final scheduling, and only if the final schedule does not meet the time constraints, we start off again at the first step using reduced overall timing constraint. So let's look at an application example. We want to build a semiconductor or system for an audio lab, which consists of several components like a mixer, a fader, an echo system, an equalizer, and balance units. And this consists of a slow spark processor and hardware implemented in a 1 micrometer ASIC library. The allowable delay of that system is about 22.675 microseconds, which corresponds to CD hi-fi quality with signals of 44.1 kilohertz. So the hardware in our system looks like that. We have the Spark processor, we have an ASIC with a 1 micrometer technology, and we can afford some external memory to store data and programs. Actually, this is far outdated technology, but we can use it as a simple proof of concept here. So when we apply cool optimization to such a system, we see that the running time of the optimizations can differ widely. So for the 3 use cases of building a 2-band equalizer with a heuristic approach or an optimal approach, the runtime is nearly negligible. It's less than a few seconds. And also for the 3-band equalizer with heuristic approach, the optimization time is negligible. However, when we try to use an optimal approach using the ILP solution for the 3-band equalizer, for several designs the evaluation time for producing a solution goes up to 1,800 seconds. A solution time goes up to 1,800 seconds or half an hour, which is rather long for solving such a problem. So we see that the running time for the heuristic approach actually is far more feasible. So we see for even more complex solutions like 7-band equalizers or the complete system, including an MPEG encoder, the solution time in seconds for the heuristic approach doesn't exceed 18 seconds, which is far more feasible than waiting for half an hour for a solution. So which kinds of designs are actually possible using our approach? When we take a look at the design space for the Audio Lab application, we can see that on the one hand we can implement everything in software. So we need 72.9 microseconds for executing our software on the processor, and of course we need no additional area since we need actually no hardware, so we have arrived at that point here. On the other hand, if we implement everything in hardware, we only need a processing time of 3.06 microseconds, but a large area of 457.9 times 10 to the 6th of area. So if we have a given sample rate of 18.6 microseconds, we can get by with a hardware area of 78 million units. So the cool approach actually shows that a formal model of hardware-software co-design is beneficial. Intellectual property modeling can lead to useful implementations even if the optimal result is available only for small designs. There are of course other approaches for applying hardware-software partitioning. So you could start off with everything, all of the functionality mapped to hardware, and then gradually moving to software components as long as you're able to keep your timing constraint. On the other hand, you could start off with mapping everything to software and then gradually moving to hardware, so building in accelerators until the timing constraint is met, or you can do a binary search on your solution space. So if we consider hardware-software partitioning in the context of mapping applications to processors, which is what this current chapter is all about, we can actually handle heterogeneous systems consisting of processors and specialized hardware components. We can handle task dependencies, because we can consider the order of tasks here. We can consider communication and memory sizes, at least in the cool system. Cool actually supports homogeneous processors only, but heterogeneous hardware units. But we have no link to scheduling theory so far. So, this ends today's presentation. Thanks for listening. Thanks for watching. Until next time.